Hello, Supriya. Hi, good evening. I think
Hello, hi, good evening.
maybe we'll wait like usual. I hope some
Yeah,
others will also join.
yeah, okay.
Did you attend yesterday's session?
Yes,
Okay, so it's going to be a repetition.
yeah, it will fix in my mind. That's right.
So I got to know that yesterday. I think there was a request that to show some software demonstration something.
Yes, yes.
Yeah,
Well,
I'm. We will release another video for that sometime later because for
okay,
today's session, that's not the agenda.
correct.
Okay, we can start then. I think others might join in time. So, again, good evening once again, and welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. So, as you know, this will be our last tutorial session for this course for this particular period. So let's get started. So here we are discussing about the contents of week 12 and how to solve certain questions based on what we learned in week 12. So mainly we learned about two things, that is groundwater recharge and flood management. So we went into very much detailed about all these things. We also looked into what are the different softwares that we can be used and what are the data that is required for each software, and how do we finally put into practice or implement whatever we have learned in all the other lectures. A practical understanding was also given in this week's content by looking into several case studies. So let's get started to certain questions. So the first question is, which factors affect the suitability of artificial groundwater recharge areas? So yeah, so do you want to take this question up?
Yes. First one is second also.
Fine. Frequency of rainfall, yes, it influences groundwater recharge. Then infiltration capacity of soil, yes.
Yes, suitability of aquifers as well, and geological formation of soil also.
Okay. Yes. So, how does suitability of aquifer actually help?
Actually, this is suitability of artificial groundwater recharge. So, if aquifers is suitable enough to be get recharged, then only groundwater recharge will happen.
Yes, yes. So basically, you need an aquifer, and that aquifer should be in a condition so that we can recharge it. Like if there is no aquifer, or if it is in a very pathetic situation, that whatever effort we do, if it cannot be recharged, then there's no point doing it. So before that, before we do artificial groundwater recharge, we need to ensure that the aquifer is also suitable for that particular artificial recharge that we are doing. And
Correct.
geological formations, how does that help?
Geological formation of soil. Type of soil is also important. Like,
Yes, yes. So
yeah,
that influences the percolation capability of that soil, the type of soil. So
yes,
certain geological formations also, that is based on the form or the material or content which is there in that soil, or basically the characteristics of that soil and the type of formation it is, that also influences on how much water gets into the aquifer. And if you're using some artificial methods, then how do we go? So based on each method, that is, if it is in a contoured land, if the geological formation is a contoured land, then we have learned about a different kind. That is, we break it into steps, and then we do an artificial groundwater recharge. If it is on a flat soil, then it's different. If it is on a loose soil, then what the artificial recharge that we're doing is different. So based on the geological formations of the soil, also we will have to look into, or the suitability is also determined by these factors. Yes, so all these are correct. Fine. Let's proceed on. Yeah, so this is from the lecture, whatever we learned. It's the same thing which we discussed right now. That is, what are the factors? And yeah, so mainly we're talking about the extent of infiltration which is happening, and all these factors affect. So as we were discussing, like hilly areas, like we'll have to use gully plugging, bench terracing. So this is what I said, stepping or bench terracing we use, or contour trenching we use. So like that, based on geological formations also, we will be looking at what are the different other suitable methods that we can use. Right. So let's proceed. Subsurface water storage capacity for artificial recharge depends on. So let's go option by option. First one, does it depend on water table contours?
yes,
Yes, it depends on water table contours. And then depth to water level during the post monsoon period.
yes,
Yes, that. And C, suitability of aquifer systems for artificial recharge.
no,
Okay. Thickness of unsaturated material available above the water table in the unconfined aquifer.
yeah,
Yes. So why not the second one?
because this is for subsurface.
Exactly. Yes. So here we are talking about subsurface water storage capacity. So for that, the suitability, the aquifer, we don't have to worry about it. Correct. And all the other factors, yeah, it depends, like depth of water level, thickness of unsaturated material. So why thickness of unsaturated material? Because saturation will also depend upon that for the subsurface. If you have like a more thicker unsaturated material, then that much of area to be saturated. So about the water, so that also influences. But yeah, suitability of the aquifer systems for artificial recharge does not influence. Fine. Let's proceed further. Identify the correct function notation for the volume of water required for artificial recharge. Yeah, so you can attempt this.
Yeah, B option.
The option, volume is equal to intercontour areas below cutoff level into specific yield divided by recharge efficiency of the structure.
Structure.
Okay. Uh, yeah, B option. Fine. So it's this one. Yeah. So this we have learned in our lecture also. So it is the volume. Okay. No, wait. intercontour area. No, whatever they asked, they've asked for identify the no, it's the volume that you're talking about. Intercontour areas below cutoff level into. Do you wanna check this once more? Like, which is the answer?
Volume.
Yeah, just give me a second also because I think there is some error in this question. So
Yes, even after seeing this slide, I'm also
yeah,
feeling
so
it.
this is the answer which I had planned. Sorry, this is the answer which I thought was correct. That is volume of water required for artificial recharge. It is this one which will come up to option D. So this is, but then I think in the previous solution the answer given is B. So which I just saw it right now. So
Yeah,
I'll
but
just
go with the bottom one. The volume will be specific yield and reciprocal of.
yeah, so that is the correct one, is what I thought. Volume of subsurface storage into specific yield into reciprocal of recharge. So that is what is supposed to be like volume of specific yield into specific yield is also there. Subsurface
Yes.
storage. Yeah, yeah, okay. So, okay, this question I will just keep a mark on this. I'll put it in the discussion forum. What is the answer for this? Because in the slides, this is okay. So this is there intercontour areas below cut. So volume of subsurface storage. So this is there. Uh, so okay, I'll get back to you regarding this question.
Yes.
Yeah. So question 4. Which statements are correct among the given statements regarding groundwater recharge? Artificial recharge reduces soil erosion, flood, and ensures adequate soil moisture. Is that right?
Yes, it is right.
Yeah. So that's the basic artificial recharge. In addition to recharging, it also reduces soil erosion and all. And B, piezometric surface is lower during artificial recharge of groundwater.
This is wrong. Actually, piezometric surface is not lowered, it is higher during artificial
Okay. What
recharge.
is piezometric surface?
There is one surface above water table, water table.
Exactly.
It's
Yes.
called. Yeah.
Yes. Yes. So it's actually an imaginary surface, like whatever where that separation happens from that water table, that we call it the piezometric surface. So yeah, it's just like a layer. So that surface so it's an imaginary surface, and during artificial recharge it increases, like we are recharging it, so there is a rise. It doesn't lower during artificial recharge. Now
Yeah.
option C, artificial recharge can be achieved by artificially changing natural conditions. Is that right?
Yeah, correct.
Yeah, so that is what we are doing. Like, because natural conditions are not adequate enough in order to recharge, we are using some artificial methods, but the whole process is the same thing. That is, you are recharging water, or you're putting in more water into the subsoil. So yeah, so now option D, artificial recharge increases inundation.
This is wrong. It
Yeah.
decreases the inundation.
Yes, exactly. So it's kind of similar to what we saw in option one. So it's just the opposite. So our answer would be B and D are wrong. So no, B and D are, what is it? Okay, they have asked for the correct answer. So A and C is the answer.
Yeah.
Fine. So yeah, so this is the notes, whatever we learned. Yeah, so piezometric surface it is a rise of the piezometric surface, what happens during artificial recharge. And yeah, so here we have all this inundation. Yeah, so it basically reduces inundation, improves infiltration, water quality, reduces soil erosion, all that. So it does not increase inundation. Fine. So let's proceed further. Match the following and mark the option for the correct match. Yeah, so let's do this.
Ditch and furrow surface spreading technique.
Okay, it's a surface spreading technique. Fine.
Gully plugs are and not P2 9, P3. It is P3.
Oh, sorry, I wrote it wrong. Yeah, P it is 3. Yeah, sorry. It's a surface spreading technique. Yeah.
Gully plugs are runoff conservation structure.
Runoff
Bore,
conservation structure. Okay.
bore blasting aquifer, gravity head recharge well subsurface.
Sorry. Gravity head recharge well, it is subsurface, and core blasting is
Yeah.
aquifer modification. Uh,
Yes.
okay, fine. So yeah, so ditch and furrow is correct. Yeah, it is a surface spreading technique. So basically, we have like we create certain surfaces like this. So on the surface itself, maximum. Yeah. So here I have images for that. Yeah. So this is the ridge and furrow technique which we'll be using, and this is the gully plugs which we will be using on the right hand side. What you yeah. So this is the gully plug. So it's basically you create certain stops so that water is stopped, like the runoff is not high. So yeah, so that you were right, like it's a uh, runoff conservation structure, correct. Then gravity head recharge wells, yeah, so gravity head recharge wells, it is a subsurface technique that is we observe over here. Uh, and the last one was, yeah, bore blasting. So this is bore blasting, which is like basically we dig in bores and we put some dynamites or something and we blast it. So you have your aquifer modified because of that. That is more areas there for water to flow. So yeah, so bore blasting is an aquifer modification method. Whatever is happening underneath, like it modifies that. Correct. So I think we can proceed further. Yeah, so this is what we were discussing in our lectures also. What are the different subsurface methods, surface spreading methods, and all that. And we have discussed these in detail. So if you want to revisit the lecture, then you can go to this slide and look. So let's proceed. Okay, question six asks which statements are correct about recharge basins. So let's go option by option. First one, option
First
one.
one is not correct.
So, recharge basins are not suitable for lands adjoining rivers or canals with sufficient non-committed water. So, we are talking about incorrect statements. So,
Yeah.
okay. So, basically, this is correct, is what you're saying.
No, this is wrong. Incorrect statement.
These are suitable for lands adjoining rivers or canals with sufficient non-committed water. So, recharge basins are not. You're saying it is not suitable.
Yeah.
Okay, fine. Why is it not suitable?
Sorry, no. This is incorrect statement.
Ha, exact.
These are not suitable. मतलब correct statement would be like these are not suitable for land adjoining rivers and canals.
Okay. So, yes. So my question is, why is recharge basins not suitable in regions which are adjoining rivers or canals? Like, why are you saying that this is not correct? So basically, this is not correct, right?
Yeah. Uh, Recharge basins are not nearby, like adjoining rivers and canals.
I mean, is there any problem if we construct a recharge basin near the rivers or canals?
Actually, near canals and rivers, the water table is already very, like, it is up as compared to the area which are far away from rivers.
Okay, okay. So, so here we are talking about recharge basins. That means we are talking about underground water recharge, right? So next to
Correct.
rivers and canals, it is a surface water which is there. It is not
Yeah,
the aquifer and it is not the underground water that we are talking about.
correct.
So that point of the water table will be high need not be valid everywhere. That just because there is a water body near to it, the underground water level over there need not be as high, because if you have heavy water draining, or if you have a pump well from which we are constantly pumping out water, the underground water table can reduce, because the recharge or whatever water we are taking, the recharge which is happening, if that is lower than the rate at which we are taking out water, then water level can go down. So that need not be true always, according to your logic. So ideally, these are suitable in lands adjoining rivers or canals because we can easily take this water from rivers or canals and using artificial or natural methods if possible, but mostly artificial methods, we can inject or put this water after some treatments or something. Like if it is, yeah, if it is rivers, maybe much treatment is not required. But if it is impure water, then after some filtration, we can put it onto the groundwater. So for groundwater recharge. So those kind of methods also we have studied. So actually, it is suitable. It is very good if you have a recharge basin or if you're making a basic. So the idea is we want the surface water to go into the subsurface level. So which will not happen in case of the surface water body. Like it won't go down, right, in that region. So we need to take that water and we need to put it down into through some other methods. And also there's one more point. So one, it is in the adjoining area, and second one, it is with sufficient non-committed water. So what is non-committed water?
I don't know.
Yeah, so non-committed water is water which is not designated for any particular use. So usually if you have a water body or river, then if there's a factory or if there's a residential complex nearby, then the water coming from that water body is usually designated for the use of that particular area for their water supply or for their sanitation purposes. So like that, most of the water supply systems from these natural water bodies are designated or committed. So we cannot use those committed water for artificial recharge because that already has a specific use. So for artificial recharge, we should ideally go for water which is not committed, like extra water which is available. So this statement of recharge basins can be located or it is suitable to be located in lands adjoining rivers or canals with sufficient non-committed water is actually a correct statement. It is required. Okay.
Okay.
Yeah. So next statement B, is it correct?
Yeah.
Yeah, so they should, and why? Why they should they have?
Gentle slope. If slope is not there, then water will penetrate underground and will penetrate easily. Not easily, like they can penetrate. Water can penetrate more to the ground. If it is slope, then they can go to the recharge basin easily. Slope, if it
Huh,
is there.
okay, okay, correct. Yeah, fine. No, basically you put a, so it's a basin. So in the entry and exit points, you are allowing water to enter and you're allowing water to exit. So if you need some movement to happen at the entry and exit points, you need a slope. Like you need, if it is completely flat, then there won't be a proper entry and exit point, right? So the slope or the diagonal is what defines that this is an entry point and this is an exit point.
Yeah.
Correct. Then option C, they should be constructed perpendicular to intermittent streams.
This is wrong as not perpendicular, it is parallel.
Yeah. Biparallel?
Uh, because how water will flow like to the streams if it is perpendicular.
Exactly, exactly. So you don't want to disturb the natural flowing pattern of the stream also. Like you don't want to go cross against it and then collide. Like you go perpendicular so that the natural the streamline continues. And option D, the rate of inflow into the recharge basin should be less than the infiltration capacity of the basin.
Yes.
The rate of, okay, just read the question once more. The rate of inflow into the recharge basin should be less than the infiltration capacity of the basin.
No, it would be more than the infiltration capacity of the basin.
Why should it be more?
Because it is talking about the recharge basin and the inflow should be more for the recharge basin rather than infiltration capacity.
Yeah. So mainly because you want some water in the recharge basin. Like if you're just gonna put something and if it just goes away at that point itself, then the whole purpose doesn't happen, right? You want sufficient amount of water to be there so that slowly it recharges, and you can keep pumping it. So that's the recharge basin, what is happening. So inflow,
Yeah.
it's usually it's slightly a bit more than the infiltration capacity of the basin. So this option is wrong. So here they've asked to find which are the incorrect options. So A and D are in. Sorry. No, so A is correct. Yeah. So they should be, yeah, so this is wrong. They should be constructed parallel. C and D are incorrect. Sorry, I marked it. Yeah, so C
Yes.
and D are incorrect. So let's just see in the less lecture also what we learned. Yeah, so these are constructed parallel to intermittent streams. So this we have discussed. And why? To increase contact time, reduce suspended material, and allowed periodic maintenance by bypassing the same. So that is why we constructed parallel to the intermittent streams. Then, yeah, so we need a gentle slope which facilitates water circulation. As we were discussing, if there's no slope, then that circulation or the movement and entry and exit will not happen. And yeah, so rate of inflow into the basin is a little more than the infiltration capacity of the basin or multiple basins. So this is what we were discussing. Fine. Let's proceed. Match the following and mark the option for the correct match. Let's go. Contour bunds.
Yes. Third one.
Embankments of land along contours in low rainfall areas. Correct.
Percolation tank is 4. Q4.
Surface water bodies created over a highly permeable area. Correct.
R is 1.
R is one, that is, can recharge multiple aquifers. Yeah, correct.
And then is second.
S, yeah, obviously. So recharge pits recharge by infiltration through the Vatosu. So yeah, so these are correct. So just to discuss contour bunds, we discuss like if we have, then we will construct certain bunds like this, and we allow water to flow through that. So we basically create certain walls, like small wall kind of thing, which we create. And we discussed about other gully plugs also, which is again similar to contour beds, but again this is constructed perpendicular, or it basically blocks the flow of water. Uh, Contour bunds just forms a frame, or it creates a bund around the water body and protects it. But gully plugs will form what do you say, if you take from the section, so it'll be something like this. So water, when it flows, it'll have to pass through this and go. So for percolation or infiltration to happen, when you have something like this, then there is more infiltration which is happening over there, because something is holding it over there. So those are the two things. Then you have the percolation tank. Yeah, so again, you need percolation to happen. So you make a tank over a very highly permeable area, so that maximum water will go down through the permeable membrane. It will go down. And injection wells also we have discussed. So yeah, so the that we discussed, like the main advantage of injection well is that one injection well can cater to multiple aquifers. And then we have the recharge pits, yeah, which is any normal, like normal pits, recharge pits we create. Correct. So let's proceed further. Okay, so this is a problem. It's a very simple problem.
Yes.
Yeah, so there's nothing to do. It's just a very mental problem, but let's do it. Uh, the average monthly rainfall volume of an area is 100 meters. So monthly rainfall, we have it's 100 mm, and rainfall being collected in a building having roof area. So roof area is 250 square meter and household size of 5. Determine the number of days, determine the number of days a collected rainwater is adequate for a building. Consider average daily water demand as 120 LPCD if the entire water can be treated and stored without loss. Fine. So let's do. So we have average. Let's go by monthly. With that is what is, yeah. So average monthly is what is given. Monthly rainfall. So that's 100 mm, and so yearly we can calculate how much would that be, or basically the annual rainfall would be 100 into 12, so 1200, which I'm converting it to meters, so 1.2 meters. And now you also have the roof area which is given, so basically how much of rainfall we will be capturing based on the area. So total rainfall that, so this is per meter, so yeah, so yeah. Now rainfall which we will be collecting in a 100 square meter area. So total rainfall that we would be collecting would be the roof area into the annual rainfall. Into the annual rainfall. So that would be, what is the roof area? 250 square meters is what is given into 1.2. So this is in meters and this is in meter square. So whatever we are getting is now the volume. So yeah, so how much does this work out to? 250 into 1.2?
500.
250 into 1.2.
Oh, sorry. It is 300.
Correct.
300 is
300 meter cube. So that is the volume that we have. So let's convert the volume into liters. That is, so meter cube to liters. So it'll be into 1,000. So basically 300,000 or 3 lakhs liters. And yeah, so now we also, yeah, so we also know the daily consumption of water. So the if the average daily consumption is 120 LPCV, so let's see the total. So daily consumption, so our daily consumption of water is equal to average consumption. Like the overall daily consumption would be average consumption in, so this is LPCD, that is per capita. Like C is also there, and we know that 5 people are there. So the total consumption would be into the number of people who are there.
yeah.
Number of people. So that is 120 into number of people 5. So we'll need around 120 into 5.
Uh, 600.
Correct. So 600. So we need around 600 liters of water for the entire family. And we have around 3 lakh liters of water. So basically, the number of days, number of days water is available would be this 3 lakh divided by 600. So how much does that work out to?
500.
Correct. So basically, for 500 days, we will have water if we harvest rainwater from the roof. So that is option C, 500. Okay. Can we proceed further?
Yeah.
Yeah. So question 9, match the following and mark the option for the correct match. Yeah. So this is also simple. Like, yeah. So fluvial flooding.
Fluvial is river overflow its bank. Is third one.
Yeah. So fluvial is river overflowing its bank. Correct. And fluvial.
Second. Coastal and second.
Rainfall creates not related to an overflowing water body. Yeah, correct. So it's
Yes.
basically from rainfall.
Yeah. Coastal is a storm
Yeah,
surge.
coastal is storm. So this is yeah. So this is easy. That is P3, Q2, and R1. So that is option B. Right. Yeah, P3, Q2, and R1. Correct. Yeah, so this might get a bit confusing. So you can always remember that this has some overflow which is happening. So it's fluvial, like it's overflowing, and then it's fluvial, so it is not overflowing. Like the other one is not overflowing. So that
Oh, yeah.
some keywords to remember, because otherwise the words can get a bit confusing.
Yeah.
Okay. So yeah, so this is the notes which we learned for that. I'm not going into details of that. So question 10. Sorry. It gets zoomed out. Yeah. Which statements are correct among the given statements? First one, is it
Correct.
first one is correct. So yeah, storm surge occurs when high winds push seawater to the coast. Yeah, correct. Now, yeah, second one,
Yes.
overland flow and channel flow can converge to nearby streams during fluvial flooding. So we are talking
Yes.
about fluvial. So what does fluvial stand for?
Fluvial is flow, overflow.
Yeah, so there is overflow which is already happening. So this one asks overland flow and channel flow can converge to the streams. Can it?
Yes.
Okay. So in fluvial, what is happening is it is because the streams are flooding, like, or from the streams only water is coming onto the roads or other areas and it is creating the flood, right? So it cannot converge to that water body because it is from the water body where it's coming.
Yes.
You get the logic. Okay, if it is a different water body, like you have one stream here and then you have another stream which is not causing the flood, then from there it can go. But usually that doesn't happen, no, because in one region all these streams would be connected mostly. No, it
Yes.
will be connected somewhere or the other. Like it won't be like you have an island stream in one and a completely unconnected stream. In the nearby regions, it won't be there. So fluvial is mainly due to these streams. So it cannot converge in the streams because it's from the streams it's coming. So you need to remove it by some other way. But for pluvial, that is, if it is coming through excessive rainwater and if adequate infiltration or percolation capacity is not available in the soil due to concrete or rigid construction which is there, then that water can be taken and put into the adjacent streams or nearby streams. That is essentially what we do in our drainage system design also. So this is not correct. That is, overland flow and channel flow cannot converge to nearby streams during fluvial flooding. No, it doesn't happen that way. Clear?
Yes. Okay. Yeah.
Okay. So that's what the trick is. It's because it's fluvial flooding. If it was asked just flooding, then maybe the statement, no, then the statement becomes very vague, like it won't be possible. But for other, and even if it was fluvial possible, if it was coastal flooding also, maybe it's possible because that's happening from the seashore or from it's happening from the sea. Whereas the river might not, or the other adjacent water bodies will not be flooded. So that also might be possible, but this is definitely not possible. Okay. Now, increase in pervious areas has increased the incidence of flood.
It is wrong. Sorry, one second. Yeah, it is correct.
Increase in pervious areas has increased the incidence of flood. So when you
Yes.
have pervious areas, what happens?
Water cannot percolate or
No, no,
like.
it's pervious. Pervious means it can percolate. Like you have a, it's more like it.
Oh, yeah. Correct. Understood. Impervious areas can increase the incident
Exactly.
of.
So impervious means it cannot, but pervious
Yeah,
means it can. So yeah,
it is
so
wrong.
yeah, so this is wrong because if you have, if it can percolate and if it can penetrate into the ground water, then it will not cause floods, right? So increase in perviousness reduces the incidence of floods. So this is wrong.
Correct.
Now, option D for 1D approach of flood modeling, surface flows are modeled as open channels or ponds and solved using the 1D Saint Venant equations.
I forgot about the what was 2D.
Yeah,
So I.
yeah, right. Yeah, so this is that software related. So yeah, so
Yes.
this is actually right. So for 1D approach, we model it as surface open like flood open channel flows and we solve it using 1D Saint Venant equations. So yeah, so this is a correct answer. So here it is B and C, which is option D. So that is the correct answer. So let's see over here in yeah. So 1D it is yeah. So this is what it is. Then for 1D 2D we go for water equations of surface flow and 1D for drainage flow. So we use this is so you said you forgot, right? So we use the shallow water equations. These are the two. So we have the Saint Venant equations and we have the shallow water equations. So this is the 2D shallow water equations which we'll be using. And for dual, again, for advanced models, we even use the digital elevation models also to find in what direction water will be flowing based on elevation. Fine. So that's clear, right? Let's proceed further.
Yeah.
HEC RAS is mainly used for, so now we are getting into very details of all these softwares and all that.
I think this was for reverse osmosis. I cannot recall.
No, so HECRA is mainly okay. One thing is we have learned all these softwares for flood management, right? That is how to see whether flood is going to happen or not. So that has to be
Yeah.
there. Floodplain management will definitely be there because that's the context. We only learned two things in this lecture or in this module: groundwater recharge and floodplain management, and all the or flood management, and all the softwares which we mainly discussed was for flood management. So that is there, and so simulation of ultrafiltration of reverse osmosis, we have not gone into those details, like because actually reverse osmosis and all mainly comes in those water purification technique. That is, if you have salinity in water, how do we purify it? Previous discussion also we discussed this. So that we have not gone into details of those. So this is HECRAS is not used for that. And water quality, so whether it models water quality and whether it models sewage treatment becomes the question then. So mainly here it models water quality. So that is one more additional aspect which we need to consider. So that is there in our lecture also, that is over here, HAS. So we are talking about, yeah. So we are mainly talking about HAS, RAS, and we are saying that in addition to flood management, we can do water quality modeling also. Then water temperature modeling, mobile sediment transportation model, etc. We can do using this software. But sewage treatment simulation we are not doing here. So, I mean, logically, again, treatment gets into more chemical aspects. So these both are actually purification or treatment related aspects, which the software cannot handle. So this looks into water quality, water management, water flow, all those aspects. So maybe we can remember that way. But yeah, remembering what are the uses of this is not very easy because there are so many softwares also which we learn. So
Yeah.
with some tricks, maybe you can try remembering something like that.
Yes.
Yeah, so the answer for this is B and D. So this is what we learned. Now, question 12, it is match the following and mark the option for the correct match. So let's do option by option. Source control measure. Okay, so basically it's a different control measures we're talking about. So can we control, we can control the source, we can control the site, or we can control the region. And so what are these three methods is what is asked. So which of this is a source control measure?
Source will be retention pound 9. I am not sure. You
So,
can explain.
okay, let's go to the next one. What will be the site control measure?
Site control can be like infiltration trenches,
Okay, fine. So site control measure is infiltration trend, and regional control measure can be.
green roof.
Okay, so can we install a green roof in an entire region?
Yeah. Your
Like, so I have a region, like I have a city or I have a town, and I want to install green roof in the entire town. Feasible?
yeah, we can.
Okay, I think the planner in you is being very ambitious over here. No, so okay, so basically green roof again, in present context, it's a very individual choice, right? Like you want to install a green roof in your residence, you do it, or you want to do it in your apartment, you do it, or some offices they want to do it, they do it. But to take it as a region control measure, like how do you go about it? How do we ensure that entire region has a green roof? Like such kind of policies cannot be made. No, it's not feasible to make a policy. I mean, you can definitely mandate saying that all the new houses coming should have a green roof and all that. Like some those policies can be made, but that is not a regional control measure for urban drainage system. You cannot say that for our drainage system we need like all of you should have a green roof. Like it cannot happen that way. So that is actually a source control measure. That is wherever. So roof is mainly where we are getting the rain from. So so that's mainly a source control measure because there itself you're controlling it. Whatever water is coming or falling in that roof, you're utilizing it for certain like growth of plants or you. So that is what your green roof is doing, or your in case, even if you are harnessing that water, you're again purifying that and then taking, because it passes through so many layers and then comes. So that's a source control measure. You're controlling it at the source. And it's again a bit more, it's more at an individual level. Like it's not at a regional scale also that we will be doing it. Whereas an infiltration pond is a site control measure, as you rightly said. So you have a site, and in that site you can do. Whereas a retention pond is more of a regional control measure, because a retention, the water in one retention pond will not come from one household, or it will not come from one office. Like it will be coming from the entire region. You have a retention pond for that entire region. So yeah, so I think so it's P is 3, that is source control measure is green roof, site control measure is infiltration trench, and regional control measure is a retention pond. Clear?
Yeah.
Yeah, so let's proceed. In flood modeling using HECRAS, Delaunay triangulation technique is used to create which of the following? It's again a bit more detailed. So yeah. So yeah, so
Boundary for flow areas.
okay, a wild guess, I suppose.
Yeah.
Yeah. Okay. So the answer is it's a 2D computational mesh. So basically, what happens in the software is you need to find the flow, right? What is happening? So you need a computational mesh, and so if you have like this much of region, so for that entire region, a mesh is made, and it can be of different sizes, like triangular, hexagon. So here they're talking about. Okay, let's not get into the method. So why this mesh is important is because from this, like from this point, where will water flow? From this point, will water flow here, or will water flow here, or will the water go to this mesh or this mesh? So that is what the software mainly determines. So it is from this mesh. So from one mesh to the next mesh, how does the flow happen? So that based on computation, that is based on all the factors that it considers, it will do that. So a mesh is very much important. So that is, so here again we're talking about 2D. We're not taking the 3D information. We're talking about 2D information. So this 2D computational mesh, in order to get this mesh, we use a Delaunay triangulation technique. So it's the technique which is used. I'm not going into detail on how the triangulation happens. Mainly it happens from like 3 points. It takes data, and then based on that it comes. Like let's not go into those details. But yeah, so this is what we discuss. So in HECRAS, we use a 2D flow area editor, which is used to create the 2D computational mesh. And this computational mesh is made by following the Delaunay triangulation technique, and then constructing using a Voronoi diagram. So Voronoi diagram, why do we use? We use it in order to demarcate the region where that water source is coming. So this we have discussed, like in rain gauge, when we were discussing, we discussed for catchment also, we discussed to get the catchment area, or the boundary of that, or it's an imaginary boundary to get. So for that we use a Voronoi diagram. So this is what it is, which we were discussing, like from this point it flows here, then it flows here. So how does that flow happen? So this is the Voronoi diagram. Fine. So let's proceed further. Data used in 1D, 2D dual drainage approach using HEC, HMSR. So, okay, basically they're talking about what are the data that we need. So do we need land use and land cover data?
Yeah.
Yeah, it is required, because why?
It is required.
Yeah, it is required. I mean, no, it's not just like that. The idea is the the flow pattern, or the infiltration, percolation, everything changes with respect to the land use and land cover data. So that is why we need this one. Now, hydrological soil group.
Soil group, yes.
Yes,
Hydrological soil
yes.
group.
So this also we discussed before. That is based on the soil type, it varies. So yes, location of elevated reservoir.
Yeah.
Okay. And D, infiltration.
Yes.
Yes, so infiltration is there, but location of elevated reservoir, do we really need that information for drainage? We're talking about drainage again.
Okay, no.
Because I asked.
Yeah, no, for drainage it won't be required.
Yeah,
For
so
water
water
it is.
supply only, it'll be required. So this software which we are using is for drainage, like for data used in 1D, 2D dual drainage approach is what we are talking about. So location of elevated reservoir is not required over here. We only need these three data. I mean, other data are required, of course, but from the options, this data is not required.
Correct.
Fine. Yeah. So this is the data requirement which we learned. So I'm not going into that. Yeah. So now question 15. In which format the digital terrain model of the river system is used as input in 1D, 2D dual drainage approach using HEC GeoRAS?
It's DEM.
Okay. DEM. What is DEM?
This is a digital elevation model, I think.
Yeah, so that's mainly used in our GIS in order to get the elevation data. So here,
Correct.
what we need is digital terrain model of the river system. In the digital terrain model is what we need of the river system and input in 1D, 2D drill. So it is not the digital elevation model, but it is the ARC Info TIN which we use. It's We use digital elevation model to get the points and then we can convert into other data types and all that. But for to get the digital terrain model, we use the ARC Info10. So there's
Yes.
not much explanation to that. It's the format that we use.
Correct.
Fine. Yeah. So this also we discussed somewhere over here that where we were talking about the different data and ARC Info10 which we will be using over here. Yeah. So we discussed the digital terrain model of the river system in the ARC Info10 format is what we use. Okay. So this is DTM which we need. DEM is the elevation model. So let's not get confused with both. Okay, fine. So question 16. In hilly areas, artificial groundwater recharge can be achieved by injection wells. Okay, so highlighters, we're talking about hilly areas.
Yes.
So
Contour bonding and bench terracing.
yeah, so this we have kind of discussed before also. That is for contoured areas, we will be using contour bunding and bench terracing. So contour bunding, bunding we have already discussed. So contour bunding is the same thing. For each contour, you construct certain bunds and you store water over there. And bench terracing is also the same way. You make a step terrace in the region so that water does not. Yeah. So basically, so to prevent water from just simply flowing like that, we make steps like this so that these regions water will be retained. And if we have a bund, then that means we'll put a small a bund or a structure which holds water in place. So yeah, so B and D are sorry, B and C are correct. Yeah, option B. Fine. So let's proceed on to question 17. Dash approach of stormwater management manages runoff at the source through distributed, decentralized, micro-scale controls. So we are looking at stormwater management that manages runoff at the source through distributed, decentralized, micro-scale controls. So water sensitive urban design, low impact development, sustainable urban drainage system, none of the above. So let's go by like from land. Sustainable urban system, no, because if it's sustainable urban system means you need to consider all the aspects and it'll be an integrated approach. Like it cannot be controlling only at the source and it will not be a distributed, decentralized. So this is micro scale. You see, it's a very small scale. So the urban development drainage system will not be at a micro scale, right? Drainage system is more uh, vast. So it cannot be this. Then you have low impact development and you have water sensitive urban design. So is it water sensitive urban design? Are you designing the urban city based on this? No, you're not. Because if you're designing as a water sensitive city, then there are many other aspects which you can look into. You're not. So if you observe in these two, they're mainly talking about a macro scale or a regional scale that they're talking about. Whereas here it's again mentioned that this is a micro scale control. So this actually corresponds to low impact development. It's given in our lecture also we discussed this is the definition for low impact development also, that is at the source, that is individually we are controlling every portion in a decentralized manner. That is it's more, yeah, it's more individual, like it's not a central or it's not at a overall master plan level, but at an individual level, you're controlling and you're improving the development. So it's a low impact development which is happening. So okay, yeah. So this is there in our lectures also. We have discussed that. Now the last question is underground gandharas are a type of
Mm, rooftop, it is not.
rooftop or ban. So okay, underground bandaras you're talking about. There can that be rooftop?
No, it is underground only.
Yeah, so it is not rooftop. Then is it subsurface groundwater recharge technique?
No,
Why?
groundwater conservation technique.
Yeah, it is a
Yeah.
groundwater conservation technique. Yeah, I mean, there's no why to it. It's a traditional method which is used, and it is to conserve groundwater conservation technique. It is. Yeah, fine. So yeah, so that's all. Yeah, so this is the definition for that. So it's what they do is these are intended to retain groundwater for longer periods in the basin by arresting the sub surface flow. So that's how it happens. Fine. So that's all for today's and in fact today is the last session. So
So,
yes, that's all about this course. So any doubts in anything? You got the exam format and all, right?
yes,
Yes. So how is preparation going?
I don't know. It will decide. It will be like on 29th what is going to happen.
It'll be fine only. It's on 29th, is it? Okay.
Yeah.
Yeah, it'll be fine only because
The utilities part, this is water drainage. If I don't study, then I can pass like 40% I can score. But for transportation, it is going to be a tough for me.
yeah, that is a bit more it's a bit more complex course. I know that.
Yes, I have to study it. Like if I study, it is okay. But this this is utilities, water is easy. As I understand, because I have worked more for this water sewerage drainage, so I
Okay.
understand. But transportation is completely new.
Okay, okay. Yeah, I mean I know that transportation was a bit difficult for me also when I was studying, so I know how it can be.
College time also transportation part I didn't do. Like in fourth semester, what will you do? So it is all time left, and this time also it is like I'm just going to study like anything and just give the exam.
Yeah, but don't worry. I mean, I think if you solve the assignments, like which you have already done, I know that because you've been attending all the classes. So
Yeah,
then you will get a hang of it and it won't be that difficult. For a person who's not done the assignments, it'll be very difficult. Very difficult in the sense because that person might be a bit lost also, like what is happening and all. But since
yeah,
you've attended everything, it should not be very difficult. Just you can just brush up all the assignments and the
yeah. That
lectures
only
and all.
just I started for like seeing the assignments only and the problem solving sessions questions. That's it.
Yeah, yeah. It'll be it'll be fine.
Yeah, let's see.
Cool then, all the best. So we
Right.
may or may not see again. So until we see sometime, it was nice knowing you as a person also. Like it was very nice interacting with you. And I'm really grateful that you have consistently joined all the classes. So that shows your dedication and that's really impressive and it's very good. So
Yeah.
keep up the spirit and hope all the best for your future. Hope you may achieve great things in the future.
Thank you.
Yeah.
And same to you.
Yeah. Bye bye. Take care.
Bye.